Welcome back my dear friends, a very good morning, good afternoon and good evening to all of you at whichever time you are hearing these lectures and whichever part of the world you are. And this course title is Multi-Criteria Decision Making under NPTEL MOOC series, which is total of 60 lectures and spread over 12 weeks, and each week we have 5 lectures and each lecture being for half an hour. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur in India. So, this is the 19th lecture, which means we are in the almost end of the 4th week, and the broader set of topics which we have been continuing for quite long time is basically about the MCDM definitions, concepts of utility theory. Just to recap, because we are going to end this broader set of topics, but I will just mention the important points. The concept of utility theory, how you find out this expected value, and there were many examples which were discussed. Then we considered different concepts of the properties, 4 properties: non-satiation, concept of risk, concept of absolute risk aversion, relative risk aversion. Then we considered the 4 different types of utility functions with their properties related to A and R separately for all these 4. 4 were quadratic, the exponential, power and logarithmic. Then we considered an important concept of certainty equivalent and how certainty equivalent can be used. Then we went into the ideas of trying to utilize certainty equivalent to map how the utility function of a person looks. And then we further on went on to geometric mean methods, and based on that how you can rank decisions. Then we found out the equivalence between normality of the returns and their concept of quadratic utility function. Then we left utility, went into safety first principle and considered the 3 principles of safety first principle. One is minimizing the probability of RP being less than RL. RL is the bound, it can be replaced by RF also. And then the second was maximizing of RL, maximizing of RP bar. So, in this lecture we will consider stochastic dominance and the concept of hyperbolic absolute risk aversion property. So, hopefully, I can go into hyperbolic absolute risk aversion property, or else it will be continued in the 20th lecture. So, I will come to the examples of stochastic dominance first order, second order within few minutes, but first the concept, maybe it is mathematical, but let us lay stress on that. Consider 2 random variables x 1 and x 2, it can be A and B also, and with their respective probability density function. But for our examples we will consider very simply the ideas of probability mass function. The ideas of trying to convey using examples would be from probability mass function, but it can be replicated for a continuous distribution also. With the respective PDF and the distribution function is basically the cumulative distribution functions. They are given for the first random variable, which is x 1, I will mark with the color blue. So, x 1 random variable PDF small f 1 x 1 and CDF of capital F 1 x 1. For the second random variable, which I will mark in say for example, green, let me use the dark green, which is x 2 for the second random variable, the PDF is small f 2 x 2 and the CDF is capital F 2 x 2. Then by definition we will consider the following properties. The 0th order dominance of x 1 over x 2 will be applicable if and only if x 1 is less than equal to x 2 for all realization of the random variables, and x 1 will be strictly less than x 2 for at least one realization. So, if I am trying to plot, I will come to the examples as I missed for the first order and second order very soon. with concrete examples. So, if I have the real line and if I find out the values of x 1, I will denote by blue. So, these are the random variables. As you pick up, they are on the real line and I am choosing the corresponding values of x 2, which are in green. So, if they are more strictly greater, some cases they are equal to. So, that means both the values should coincide, which I am marking here. So, in that case you have the 0th order dominance of x 1 over x 2. X 1 is the blue one, remember. So, let me denote x 1 and x 2 was the green one. Sorry, the color did not change. Yes, this is x 2. Now, as I said, we will come to the first order and second order dominance, stochastic dominance using two random variables x 1 and x 2 and consider for the example. Now, the first order dominance is true if and only if of x 1 over x 2, if the probability of x 1 being greater than y is some value, is less than equal to probability of x 2 being greater than y for all y's on the real line, such that there exists at least one y such that rather than less than equal to, the less than in the strict sense prevails. Now, what I want you to understand is this: if I consider the probability is less than, in the sense, let me write this. So, if probability of x 1 minus y is less than equal to probability of x 2 is greater than y, this is greater than. So, they are greater means onto the right hand side. If I am looking at the real line from my side, so random variable increases onto the right, it decreases onto the left. So, probability being greater than x y, which means that 1 minus that would be onto the left hand side. So, I basically put 1 minus first, if I when I put the minus sign, this inequality would change. So, the inequality for a minus sign, so minus a minus, it becomes greater than equal to, then I add 1 plus onto the left hand side, a plus 1 onto the right hand side also. So, based on that, when I find out, it will be the probability here, now it is a greater than sign. So, it means the probability of x 1 being less than y, not greater than, because I have put the inequality and added a 1 and first I change the sign, would be greater than probability of x 2 being less than equal to y, which means if I draw this diagram, let me make a blank slide and then do it accordingly. So, this part I will again do it in the blank slide, I will discard it and do it. So, it is easier for us to understand. By the way, the blank slide which I am going to create would not be there in the slides which are uploaded, they would be there in the video. So, you can understand, because the lectures slides are written systematically, any extra portion I am just writing. The blank slide why I am creating, because the space is limited, as you remember in the earlier class which I did. So, here I will write the probability I will again write the small set of definitions and derivations. So, it is easy. So, probability of x 1 so, this was the case for the first order Stochastic. So, I make it minus sign reverses minus sign I add 1 greater than sign remains. So, 1 minus basically now becomes probability What does this mean? The last statement, which I am putting a red arrow. So, if I consider the distribution, consider the real line, there are two distributions. I denote one by green and which is, say for example, x 1 and the other one as blue, which is the y 1, which is x 2, and this is the mean value. This is the mean value. So, what I want to ensure is there is some value of y, which I will denote by red, and consider I am taking y as say for example, fixed, it can change, is the overall probability of x 1 being less than y onto the left side, and which would always be more than the probability of x 2 being less than y. The probability of sense it you are trying to cover more. The second order dominance would mean when I find, so this first order dominance basically does with the distribution function. The second order dominance means for x 1 being greater than x 2, if only if the integration of the whole area of the cumulative functions of x 2 is greater than y minus probability of x 1 is greater than y is always positive for all y, and this greater than equal to 0 is strictly greater than 0 for some y, that second order dominance would hold true. So, at least one in both the first cases should be greater and the second shade should be greater, not greater than equal to in both the cases, would give you the actual concept of first order, second order correspondingly. Now, few conditions I will state without proof. The first order dominance, stochastic dominance of x 1 over x 2 is a sufficient condition for the second order of x 1 over x 2. So, obviously, if I have the first order, second order, third order, so on and so forth, this concept of sufficiency conditions for first to second, second to third and higher orders can be made accordingly. The second point is x 2 is a mean preserving spread of x 1, then if that is true, then x 1 would be second order dominated over x 2. And what we mean by mean preserving spread is basically a change from one probability distribution to the other consider from A to B, where B is formed by spreading out, because the probability total sum is 1. So, what we do is that by spreading out B, by forming out one or more portions of A's probability density function, such that leaving the mean value unchanged, we just spread it out more. So, to make things easier, let us consider two different examples diagrammatically. I am not going to use any equations. The red one which you see is the uniform continuous case distribution between -2 and +2, and obviously, if we know the mean value is given by A plus B by 2, and if I consider these values for the red, the expected value is 0, as shown here by the black vertical line, where I will put a red tick mark. So, this is for the red one, which is x 1 distributed uniform -2 to +2. Now, consider the distribution x 2 with the same expected value, which is also the vertical black line, and I will use the dark blue to denote x 2, and it is spread between -3 and +3. So, x 2 is distributed uniform -3 to +3, again the average value would be 0. So, 0 is fixed, mean value is fixed, for B is much more spread out, if you can see, spread out more, while the first one. So, this horizontal lines are 0. So, actually the distribution is this. So, this would be the concept of means preserving spreads, and if x 2 is a mean preserving spread of x 1, as in the diagram where you have the uniform distribution of -3 to +3, with respect to that x 1, which is the first distribution, then x 1 will dominate x 2 in the second order sense. Let us consider a second diagrammatic representation. The first one is basically in the blue color is for standard normal deviate x 1, which is distributed, if I will use the blue color, x 1 is distributed normal with 0 1, and this is the distribution which you see here self. And x 2 if I consider such that both the mean values of x 1 and x 2 are same, because they are given as 0. So, x 2 is normally distributed with 0 2, and the distribution is, I will just mark it once, this is the distribution. So, if x 2 is the mean preserving of x 1, then x 1 strictly in the second order sense would dominate x 2. Now, the question is that just for your information, you saw the examples where the mean values were 0. So, is it necessary for the mean values to be 0? No, I could have basically taken any other distribution for the case of discrete and the normal case with different means. So, if I consider this example, maybe I could have considered x 1 as normal, say for example 3 standard deviation of 2 or variance of 2 square, and x 2 can be the second distribution normally distributed with 3 also, but the spread is more, consider it is now 4 standard deviation or 16 is the variance. So, this can be also done. Similarly, for the first example, I need not choose the mean value as 0. It could have been, say for example, x 1 uniform between, say for example, -10 to -5. So, obviously, the average value would be what, -10 minus 5 by 2 is equal to minus 7.5. Similarly, I could have x 2 done accordingly, which is uniform, and in that case I want to ensure minus 7.5 is the value. So, I could have had, say for example, minus 12 and the values would be, say for example, if it is minus 12 and minus 3, so the value is minus 12 minus 3 by 2 is basically minus 15 by 2 is equal to minus 7.5. But if in the second case, which is the violet one, the spread is much more. In the red case, it is much more concentrated. So, the values would give you the idea of mean preserving spread such that x 1 will dominate x 2 in the case where the example was the discrete distribution and for the case when the distribution is considered as normal. I just thought these two examples would be good one to illustrate. Now, till now I have mentioned about stochastic dominance, but I have not discussed the examples. So, these are the examples one by one for the stochastic dominance for the first order and the second order. So, let us consider the example as such. So, there are states of nature which we denote by 1, 2, 3, the outcomes, what is the probabilities, and there are two different decisions. Decisions I will denote by A and B. Now, the amounts of the outcome for the states, I have taken arbitrary values, they can be changed and you can formulate different problems to illustrate that. Other idea is that question would be that states of nature is only 1 to 3, can they be more? Yes, they can be more, they can be less also, they can be 2 outcomes or they can be 4, 5, 6 outcomes also. And decisions I have taken as A, B, they can be more than 2 also, like A, B, C, D accordingly, but I have made it simple. The amounts are given for state of natures as 10, 30, 70, and as per the decision A and decision B, the corresponding probabilities for decision A for the states of nature of 1, 2, 3 are, I will mark with the different color, see for example, red. The probabilities are 0.4, 0.60 and you see the probability sums up to 1. Obviously, it has to be decision A is out of the state of natures only, they cannot be anything outside. Similarly, if I consider decision B, I will use a green color, the corresponding probabilities are 0.3, 0.3, 0.4, again the sum is 1. Now, I need to find out the expected value first, I am just giving. So, the expected value for decision A would be what? 10 into 0.4 plus 30 into 0.6 plus 70 into 0, because the last probability is 0, the value comes out to be, using the same coloring scheme, comes out to be 22. And when I use the expected value formula for decision B, the corresponding values are, which I sum them up, is 10 into 0.3 plus 30 into 0.3 plus 70 into 0.4 and the value comes out to be 40. Now, let us draw the step functions of the decisions accordingly along with the expected value for decision A and decision B corresponding to the states of nature 1, 2, 3 separately, and then I merge them. I have used different colors so that you can understand them. Now, consider F 1 is for x 1 which is blue in color and F 2 which is x 2 is red in color. So, if I consider the corresponding probabilities, so this consider only on the blue line. So, if I consider the blue line, the jumps are accordingly. Jumps are how? If I consider the decision A, it is 0.4 first and then the jump happens 0.6. So, the cumulative values are 0.4 and 1. Where is 0.4 is happening? 0.4 is happening as the state of nature amount is 1, amount is 10, state of nature is 1. And the second jump is happening, which becomes the cumulative distribution function becomes 1, is happening at when the state of nature is 2, where the amount is 30. So, here it is 10, 30, 0.4, 0.6. Let us see. For the blue one, it is 0 till 10 and there is a jump. So, the jump happens of 0.4 if you remember. So, the jump happens here. I should use, so this is the, I should use the red color, black one to denote. So, this is the first jump of 0.4. Then it is constant, then when the value 30 occurs, it jumps by 0.6 and it becomes 1. So, the blue one is basically for x1, which is decision A. Now, consider, let us consider decision B. What are the jumps? Jumps are 0.3, 0.3, 0.4 at 10, 30, 70. So, at 10 it becomes 0.3, which is the red one, continues till 30, again jumps 0.3, becomes 0.6, continues till 0.70 and then jumps 0.4. So, 0.3, 0.3, 0.4. Now, the interesting part is two things. Number one, we see the expected value of x2, which is 40, which we calculated, and the expected value of x1, decision A, is 22. But interestingly, throughout the distribution, x1, which is the blue one, always dominates. And how I am saying it dominates? Because wherever you see in the graph, the blue line for x1 is always above the x2. So, which you see here. I will just mark it, this portion, obviously it is more, again this portion is more. So, there is no portion of x1 which is blue one is below the red one. It can be equal, in many of these cases we can formulate the problem, but it would never be fall below the x1 if x1 strictly dominates or dominates x2 in the first order sense. And obviously, if I am going to consider in the strict sense, not in the greater than equal to sign, in the strict sense for x1 dominating x2, I will draw the graph. I did not draw the theoretical one, because for the practical one it will be easy for you to understand. If I draw the graph, consider the axis is given, where the axis are along the x, you can, I am plotting the amounts as usual or the decisions based on which I am trying to find. And if I plot x1 like this, because if you remember the probability is always 1, it cannot exceed, and x2 as the blue one, ultimately the probability will be 1. In this case, the red one, which will denote by x1 with respect to the blue one, which will denote by x2, x1 strictly dominates x2 throughout, because there is no portion it is equal. Equal to sign, if you remember, would be for the case when it is not strictly dominating. So, with this I will end this 19th lecture and continue discussing about the concept of stochastic dominance further on. Thank you very much and have a nice day.